So, we have the first quiz coming up and the first test coming up. Quiz 1 is next Monday. I think that's the 29th. And exam 1 is Friday. I think that's 2-1, 2-2. Okay. I need to think about what topics are going to be on this, so let me just get back to you on Friday, or maybe I can put it up on D2L before then. But I need to look at what problems are where and stuff like that. All right, so last time we talked about stress transformations. And what stress transformations are about is you have the stresses in one coordinate system, and you want to re-express them in another coordinate system. So you want to re-express that state of stress in another coordinate system. And the formula for that is that the stress tensor in the new coordinate system is equal to the rotation matrix times the stress tensor in the old coordinate system times the rotation matrix transpose. One thing to notice here is that I didn't give you a way to do a strain transformation. That's because strain, remember, at least with this definition of strain, is not a tensor. So if you want the strain, so let's say you have the Voigt strain in one coordinate system, and you want to re-express it in another CS, another coordinate system. Steps that you have to make are first, calculate the Voigt stress by multiplying the stiffness matrix times the Voigt strain. Okay. Now that you have the stress, go from the Voigt stress to the stress tensor. Just put it into the matrix form. Then find the new stress tensor in your new coordinate system as Q stress old. Well, I guess I just called it stress, so let me erase that. Q transpose. then fourth, go from that new stress tensor to the new Voigt stress. And then finally, the Voigt strain nu is equal to the compliance matrix times the Voigt stress in the new coordinate system. Okay, so you got to go. If you want to do a transformation of strain, you have to do it through the stress transformation. That looks like a pain, but it's fast if you have all those programs in there. Boop, beep, beep, boop, beep. It sounds like that. You're done.
What if we can't get the in our calculator and we just go beep up?
Yeah, it makes it sound like that too. I've heard that before. Any questions about that?
So that's the process for one problem.
I don't know if there's a question like that where you're given the strain and you have to transform it, but there are definitely ones where it asks you to go to a new coordinate system and then calculate the strain in the new coordinate system. I don't know if there's one that has you start out with knowing the strain and go all the way back to stress, back to transform. That would be a good exam question. Okay, so now we're going to talk about the main reason that stress transformations are useful. Is principal stresses. Okay, so here's the idea of principal stresses. For any state of stress, so this isn't just possible sometimes, this is always possible. There is a coordinate system where first the stress has no shear stresses. So that means the only non-zero stress values are normal stresses. Okay, so what that says, for example, if you have a state of stress that's like this, and this, and this, and this, and this, and then symmetry. Let's say you got one of these. That means symmetry does this. Symmetry says this, and those all have values. Okay. There's some orientation of the coordinate system. Okay. There's some coordinate system where all you get is, I guess I don't know what the signs of these would be, but say you got one like that, one like that, and one like this. I'm not even going to try to guess at what the signs would be. So I don't know what orientation that is for some general case like this, you know, but it could be like 31 degrees that way and 26 degrees that way or something. But there's some coordinate system orientation where you can represent that state of stress with no shears at all. Okay, that's a pretty surprising result. Like, here's you when you hear this. Well, that's lucky. That was sort of like Goofy, wasn't it? Yeah. Oh, wait, Goofy! There's no shears in this dress. Well, I don't know how that's oriented. So as far as I know, that's like 86 degrees, almost like, I don't know. I didn't even try to guess what those values would be. But I'll show how to do it. So no, I don't know that they would all be positive like that. They could also be compression, you know. So it could be positive here, negative here, or something, but I don't know what those are. But what I do know is there are no shear stresses at all, and that's amazing, you know. So that's lucky, but that's not even the half of it. This is an amazing fact, amazing set of facts. But there's more. So second, that means then there are three normal stresses, right? The X, Y, and Z normal stresses. And one of those stresses, one of those three normal stresses, is the maximum normal stress out of all coordinate systems. By maximum, I mean like we don't know whether it's positive or negative, but it's either the maximum tension, in other words, the biggest positive value, or the smallest compression if there's no tension. You know what I mean? So if all of these are compression, you know, you could have a state where all of these normal stresses are in compression, then you're just going to have a smallest one of those is going to be your maximum. Or they could all be in tension, and then your maximum is going to be the biggest value of tensile stress. Okay, that's pretty crazy. Like, Yes, absolute value. It's a maximum. Maybe I just made that more complicated, you know. But it doesn't have to be, that doesn't mean that it has to be positive. It's just the maximum. Um, okay, so uh, there's this coordinate system where you only have normal stresses, and furthermore, one of those normal stresses is bigger than you can find with any other, you know. What are the odds of that? I mean, there's infinitely many coordinate systems. It's impossible that that would happen. But that's how it is. Cool. Why is that? That's a good question. I'm not even going to try to answer that. I wonder if I've probably seen a proof of why that is, but I wouldn't begin to know where to. Well, that's amazing, but there's more. Yeah, an infomercial. Right. How much would you expect this coordinate system to cost? $49.99? $39.99? No. Yeah. He's dead, I think, isn't he? Um, yeah. A different one of those three normal stresses is what? Yep. The minimum stress out of all coordinate systems. And now it just sounds like I'm just yanking your chain. This is like too good to be true. So you can, in other words, if there's tension and compression, one coordinate system shows you the maximum compression you have if you have a material that's very susceptible to compression. A different one tells you the maximum tension if it's very susceptible to compression. But wait, there's more. A third one has to be in between those two. The third. The. Okay, so in between is boring, but it allows you to find the coordinate system with the maximum absolute value of shear stress. Like I said last time, very brittle materials are very susceptible to breaking in shear. And so being able to figure out something about the maximum shear stress is really important for predicting failure in a lot of materials. Okay, so we have the max tension, the max compression, and one that's sort of like gives us a path to finding the maximum shear stress. And actually, so this number 4, that one normal stress lets you figure out the coordinate system where that max shear stress is, but it turns out if all you want to know is the maximum shear stress, you can just calculate that from the other two. So number 5, it's crazy. This may be the craziest thing in all engineering ever. Yeah. The maximum shear stress well, now I have to say no, but if you would have just done that, and I probably would have marked it right. But the maximum shear stress possible out of all the coordinate systems, I'll call that tau max, is equal to sigma max minus sigma min over 2. And so if you have a brittle material that's just straight going to break because of shear stress, this will tell you, and you calculate those principal stresses for your state of stress, use that formula, calculate the max shear stress, compare it to some maximum allowable shear stress for that material. And that'll just tell you it's going to break or it's not going to break, you know. And then the last one, to find the coordinate system maximum shear stress, and I should say absolute value because it could come out positive, it could come out negative, but there's no important distinction between positive or negative shear stress. So they're all the same to us. Let's say what we want to do is transform the full stress tensor into a coordinate system that's rotated 45 degrees about the axis of the middle principal stress. That's a pretty sloppily worded, ugly wording for that, but I'll do some examples and you'll see what I mean. Yeah, exactly. With 1999, you also get this. You also find out about. Yeah. All right, so. Yeah, you might have to. That's true. Yeah.
So
for 1999.
The payments that you originally weren't going to charge.
Yeah, that's true. Okay, so let's derive what the idea of this principal stress. So this is a derivation of principal stresses. I wouldn't really think that this was so important to go through, except this is, I think, for most of you, or a lot of you anyways, the first eigenvalue eigenvector problem that you'll see. And these are going to come up all the time in classes, pretty much starting now. You know, you'll see it in your next class and the class after and whatever. So this is an introduction to eigenvalue eigenvector problems. Okay, so remember that any stress tensor times an outward-facing normal is equal to the traction on that face. Okay. And so if we're trying to find a stress tensor where there aren't any shear stresses, what we're trying to do really is find three orthogonal faces where that traction vector only has a component perpendicular to the face. Okay, so to find the principal coordinate system, so we want three orthogonal unit vectors n where where the traction vector is parallel to n. Okay, think about that for a second. So on a given face that does what we want for this principal stress tensor, the outward facing normal points out of the stress cube, and we want the traction vector on that face to either point out of or into the face. So we want that traction vector to be parallel to n. So what we want, like in other words, if the starting stress, this arbitrary stress tensor, is sigma, we want to find an outward-facing normal and a constant lambda where the stress tensor times that outward-facing normal vector so this would give us the traction, is equal to some constant times the normal. So that's what we're looking for. Any questions about that? If you have anything you want me to clarify, we can take a minute to straighten that out. But so what this is saying is, so n is identifying a face, because that's any unit vector is an outward facing normal to some face. Okay, so if you choose n, you identify a face. And this is a constant. It can be positive or negative. But if you have a vector times a random number, any number, that's going to give you back a vector that's parallel to the original vector. So this is saying that the traction vector on the face associated with n is parallel to n. Okay. All right, so this is what we want to solve. And this is we can think of this as the starting eigen value eigenvector problem. Where lambda is called the eigenvalue. And I'll say well, there are three of these.
So it's eigenvalue.
No, an eigenvalue is the three lambdas. Oh, I think it is one word. Yeah, I think in German, like everything is one word. Like you yeah, you combine everything. Like Farfignugan actually means like 50 things. And the outward facing normal is the corresponding eigenvector. And it's funny that this is the case, but this problem comes up a lot of different ways in mechanics. And so, I mean, you can use it to calculate axis of rotation if something's, so you're going to see this in a lot of different contexts, but it's always going to start with this form. A matrix times a unit vector is equal to a constant times that unit vector. Okay, and it's surprising how often it comes up, but sort of having some understanding of this idea will be useful. All right, so how do we solve this? Well, first you can think of this as so I'll rewrite this equation as sigma n is equal to lambda times the identity matrix times n, where this identity matrix is 1, 1, 1 down the diagonals and zeros everywhere else. Why do you think that's called the identity matrix? What do you think happens if you multiply a vector times the identity matrix? You get the same vector, yeah. And so that doesn't change anything about the formulation, but when I So now I'm going to subtract the right side from both sides here, and you get sigma n minus lambda in is equal to 0. And then I'll distribute out the n, and you get sigma minus lambda times the identity matrix times n is equal to 0. And now if I expand that, this comes out to be sigma x minus lambda for the first element, then sigma xy, sigma xz, sigma xy. Then the yy element is sigma yy minus lambda, sigma yz, sigma xz, sigma yz, and then the quantity sigma zz minus lambda. So that matrix times nx, ny, nz is equal to 0. Oh, yeah, really? Did you see something like this? So what does it take for this to be solvable? And keep in mind that yeah, so what we don't want is for a meaningful solution, we don't want this matrix to be invertible. Why don't we want that matrix invertible? Because if there was an inverse to this matrix, we just multiply both of these two sides by the inverse of this, and we'd come up with this eigenvector is equal to, you multiply the inverse times the 0, you get the components are equal to 0. That's a worthless equation. Okay, so we don't want that trivial solution. Okay, we want the ones where you can't get a solution by inverting this matrix. Wait, so what does it take for that matrix to be non-invertible? That's right. That's right. Yep. So we need the determinant to be 0. And that determinant, okay, so our problem then is, I'm going to rewrite these. So sigma xx minus lambda, sigma xy, sigma xz, sigma xy, sigma yy minus lambda, sigma, nope, yz, sigma xz, sigma yz, and then sigma zz minus lambda. that determinant has to be equal to 0. So first, let me remind you how to calculate determinants, or maybe you've never had it, but either way, it's easy to calculate. So let's say, so here's how you calculate the determinant of a 3x3 matrix. If your matrix is A, B, C, D, E, F, G, H, I, that is A times the quantity EI minus HF minus B times DI minus GF plus C times the quantity DH minus GE. So you go, I'm just going across the top row one by one. So first I'll cross out everything in A's row and A's column and do this sort of crossing thing. E times I minus H times F. And then when I'm done, and that's that first term. And then when I'm done with that, I'll go to B, cross out that row and that column. And what's left, I'll go cross minus across, two, minus two. And then don't forget that Y always has to be the weird one. So you get the negative. And then for the third one, cross out this row and this column, that times that, minus that times that. And I think most of your calculators have a determinant function built in, but you could program it too. You could also go down the row if it's easier, you know. So that's also equal to A times EI minus HF minus D times quantity BI minus HC plus G times BF minus EC. That's probably enough ways to do it for anything we're going to do. That's right. Yep.
Value times the determinant of a matrix.
Right. Yes, that's right. And just remember, the second term you always have to make negative. Okay, so if you do that, so back to our determinant. You get this ugly thing. So you got the quantity sigma xx minus lambda times the quantity what? Well, this actually is still, so this is all kind of ugly because this is like our A. And so in here we're going to have, oh yeah, you're right, exactly, yes. Sigma, yes, you're right. sigma yy minus lambda times sigma zz minus lambda sigma yz squared, and then minus sigma xy, yep, sigma xy times sigma xy times the quantity sigma zz minus lambda minus sigma xz times sigma yz plus sigma xz bracket sigma xy sigma yz minus sigma xz times the quantity sigma yy minus lambda. And all that has to be equal to 0. In general, solving this equation is finding the roots of a cubic equation. And because it's a cubic, you get 3 roots. We'll call those lambda 1, lambda 2, and lambda 3. Then to find the corresponding eigenvectors, I mean. Plug each eigenvalue into, I'm going to number this equation. So I'll call this equation star. Yeah, new page, new color, all that stuff should work fine on your tablets. Losers. Yeah, exactly. Yeah, like, oh yeah, we're like rolling in the bucks here, us community college instructors. So one by one, you take each eigenvalue, plug it back into this equation, and solve for, so you plug it back into equation star. Solve for the unit vector n. And by the way, it's only so it's only unique down to a negative sign. So you could get a value n So if one solution is 1, 0, 0 for this unit vector, the other one would be negative 1, 0, 0. You always have a vector and its opposite. That's fine. It doesn't matter which one you choose. So of all these steps, you might, wonder like, what do you have to do on these problems? So I wanted to go through this derivation, but really all you have to do is to solve for these things. Where's the start of this? Is take this original matrix, that could have 6 independent values, 9 non-zero values, and have your calculator give you the eigenvalues and the eigenvectors, and that's it. You don't have to go through any of these steps. Your calculator will do that. But this is just supposed to be what it means, what it's doing. Any questions about that? Not even that. You're just plugging in this sigma and just saying, give me the eigenvalues, and then after that saying, give me the eigenvectors, and using those. Yep, write it down. Each eigenvector is normal to a face, and they turn out to always be 3 perpendicular vectors. So they can give you a new basis for a coordinate system, a new coordinate system, and that's the principal coordinate system. All right. So let's stop there, and then next time I'll do some examples. The best way to get ready for the quizzes, quizzes can have 2 types of things on them. Mostly it's going to be short answer questions about what I said in lecture. So skim through the lectures, especially pay attention to the things that say notice or this is important, or, yeah, like any of the stuff that I'm like trying to make a big deal out of, or any like lists of things. Those are good things to remember. So those are just going to be short answer questions. And then also sometimes I'll have you redo a question that was asked in the assignments. So you might want to skim back through the assignments and just like mentally remind yourself like how to do this and that problem. Okay? All right, see you Friday.